Belts stretch. They can take the misalignment and I can pry them on. Indeed, belts are rubber or some kind of elastomer material, but they also have a solid cord inside them that does not stretch. So they're not rubber bands, but people treat them like they are rubber bands. They have a dimension to them. The dimension is driven by the design of that belt and is also limited by these cords. And if you try to stretch them, you can break the cords. If you break the cords, you change the integrity and the structural strength of that belt and how it's going to behave. There is some flexibility here, but it does not eliminate the need for precision alignment. Why? Because if we don't precisely align the belt drives, those forces are then transmitted to all of the components in that drive. Misaligned belts will wear rapidly, and that causes damage to sheaves and bearings. So this is about treating the whole drive and having high expectations on reliability of that whole drive. Here's the other one, right? Sheaves are made of steel and the belts are rubber, so I only need to worry about the wear on the belts. Well, sheaves can wear as rapidly as belts. They can. And we can see that if we take the time to look. How do we figure that out? Well, there's a thing called a sheave gauge. Very simple, inexpensive devices that are typically made of plastic, but they have the precise dimensions of the design for that sheave and belt based off of its designation. So we use these gauges and we hold them right down in, and then we look at the gap and they should fit tight. The sheave should conform to the angle and depth of the gauge. And if it does not, it could be because you have some things like you just have the surface wearing around. Sometimes it scallops. And that's because of the wear that's taking place. You've actually lost metal material. And when you don't have that flat surface and you have a scalloped edge, now you may say, well, the belt looked terrible. I'm just going to throw a new belt on there. Well, that new belt is now engaging in that scallop pattern, which means that the forces are on a very, very much smaller surface area, and you're going to go right through and damage those belts very quickly. In severe cases, where there was severe wear to the sheaves, I've seen belts flip upside down in a matter of minutes after being installed. They'll actually flip around upside down on you. How does rubber wear out metal? How can that happen? Well, sometimes it's dirt and debris. You get a little bit of dirt and debris and it embeds in that belt, and now that starts to go to work, and a very abrasive surface starts to grind on those sheaves and wear that away quite quickly. Okay? So what else? Well, I'd rather wear out a $100 belt than deal with something major. It's easy just to change those belts in there. Well, keep in mind that a broken belt is just a symptom. It's a symptom of something else in this drive that's not right. Okay? A belt can be worn by a worn sheave. It can be worn by a mismatched sheave. You might have an A sheave and a B belt. They're not going to engage. You're going to wear that belt out. Replacing just the belts, if that's what your strategy is, it restarts the failure immediately. If you've not addressed the cause of the belt wear and you put a new belt in, it is immediately in a failure mode. And if belt drives are not optimized, the bearings can take a beating too. And these things can take it out on the bearing. And now you've got bearing issues, which can be a significantly greater amount of effort that's coming for you down the road. Now, Pareto analysis requires that you've been keeping track of what causes failures. And if you've been keeping track, then you can go back and categorize them and see where your bad actors were. But you'll be somewhere and someone will say, I don't need a tool to tension the belts. I get it by feel. Somebody said, I just push on it, and if it deflects 1 inch, then I know it's the proper tension. Deflects 1 inch with how much force? Right? Maybe you had a long day and you're not feeling as strong, and you push so far and it goes 1 inch. So I don't really know what that means. I push it 1 inch, and that's how tight it needs to be. Belt tension is only valid by 2 methods. One is the deflection of a belt a set distance while applying a measured force. That's 2 aspects, right? You can't just push on it and see how far it goes. It's a measured force and a set deflection. The other way is by measuring the resonance frequency of the tension belt. Tension is one aspect of setting up the belt drive, and we achieve tension by moving one of the 2 sheaves, right? We move it closer or further apart. Typically, it's the motor. The motor can be moved back and forth. Now, sometimes the moving of the motor is not very convenient. We're loosening up bolts and we're trying to slide it back. That's it, now get them all tight before it moves a little bit, right? Sometimes there's a real nice setup. We'll have a motor base with jack bolts, 1 or 2 jack bolts that can move that and hold that in position. We can check the tension and the alignment. Tension and alignment must be achieved simultaneously in a belt drive. You can't go after one and then go back and try to go after the other because both require movements of the sheave. Okay, I always use those cog belts because they are more expensive and better quality. Okay, now there's different styles of belts. Okay, there are synchronous belts or V belts. Synchronous belts would have drive sheaves and driven sheaves that would have teeth on them. And there are teeth that fit that on the belt. And these are synchronous in that, there's no slippage possible or involved. And then you have the V belts. Now the V belts can be smooth so that they have that profile that I showed before. I've heard people say, well, they're more expensive, they're higher quality, so I'm buying them because I want my belts to last longer. The reason belts are made that way typically is for small diameter sheaves. And what happens is when you try to make a tight bend, the material starts to kind of get in its own way, so that it's kind of relief cutouts. So really, it's important to understand, should I be using that type of belt or shouldn't I around that? So again, it's about knowing the right belt for the application. Also, about the belt size, the tooth size and spacing if it's a synchronous belt, the belt cross-section that could be A, B, C, there's all these different size designations, and they have to be right for the application. It's based on the horsepower and the speed and the energy that you're trying to transmit through the belt drive. So they must match the application. Here's another one that I've heard. These units came with variable pitch sheaves, and we always use them if we have to replace the sheave, okay? Because how often does your maintenance department or the planner find out that they need to do a replacement? They walk out, they look at the part, they write down the part number, and they order that for the job repair. Okay? If it was the wrong part out there to begin with, it's going to stay there. And we had found some of these variable pitch sheaves in facilities that had been operating for 10 to 15 years, and they had never changed out the variable pitch sheaves. What happens if I leave a variable pitch sheave in there? I get high vibration, I get belt wear, and I get bearing damage. Okay? You get really wild forces because it's not a perfect diameter that belt goes through, and a lot of times you look at them, they're sitting there and they're like cranking on the bearings as that diameter changes as it makes a rotation, so it can be very damaging. Okay, when the flow balance calls for a higher fan output, we change the sheaves. Well, so anybody remember hearing about SARS back in like the 2003 or time frame or so? And I was at NIH at the time, and there was a lot of concern that this was going to be the outbreak like we're experiencing now. So they went into NIH and said, we're going to create a SARS isolation ward. And to do that, we have to increase the exhaust fan rates. So they went through and just put bigger motors in, right? And that's how they were going to accomplish that. They were using a large motor with a small drive, putting a small little sheave on there to get the speed up, and this huge speed up drive. And it creates a lot of forces and so on. The fan, it was headed towards failure, there's no doubt about it, and it could have been catastrophic. If there had been an outbreak of SARS, right, that fan would have run for several weeks until they got all those people in there. Then they would have lost the exhaust pressure. Since they're not oil lubricated, there's no way we'd really sample and analyze grease in a bearing. Can you see where the oil went here? In fact, on the pedestal that this sat on, there was a sheen of oil down the front of it. So the grease wasn't grease anymore, it was just the soap thickener. The oil was outside of that unit. And the thickener cannot protect the rolling element from the raceway. So it had metal-to-metal contact. That metal-to-metal contact causes oxidation. Oxidation causes iron oxide, which is reddish dust, and that's what we saw here. So we took grease samples. We went through and we took grease samples of the other 9 air handlers. And out of those 18 bearings, we found 6 of them that also had mixing. So what do you do about that? We've got a mixture of incompatible greases, and now we know what could happen or might happen. Well, we implemented a purging process. So what we did was, and this was like the end of the week, so we said on Monday, here's what we're going to do. In the morning, we're going to come through, we calculate the volume, we're going to put 7 pumps of grease into each of these bearings. The next morning, we'll come back, we'll pull the grease that purged out, and we'll test it. And after day 1, still a mixture of grease. Day 2, still mixture. But when we got to Friday, 100% of the correct grease in those bearings. So it took us the week to do that purging. Now, why didn't we just put 7 days worth of grease in all at once? Okay, because you can create incredible forces, you can create damage and so forth. So this allowed the time and the pressure relief for that old grease to get out of there. The bottom line is I was still working there 6 years later and we had no further failures. Those bearings that we identified with the mixtures and properly purged them out continued to run for years to come. So the grease analysis in this case provide us the root cause and identifying the systemic issue of grease mixing, and then a way of getting in there early and correct the condition so that we don't have all these bearing failures to deal with. Okay, so another one is, okay, I can test the grease and I can take a sample. So to test the grease, I just need to dissolve it and analyze it like an oil sample. I'll just put it in my oil bottle and send it to my oil analysis lab and tell them analyze that as well. Well, it's taken some time, but we've come to realize that oil analysis techniques cannot be effectively applied to greases because they're not the same material. And even the critical properties of the grease change and are different than what are critical for oil. Therefore, we can't just apply those issues. So we've got different parameters that we're really wanting to understand. And there are now, today, ASTM standards for laboratories to apply the proper testing. So what I'll say to you as an asset owner, demand them. Demand that level of analysis that is correct for greases. We want to look at consistency. Now that's unique to greases. It's not a parameter of oils, but the consistency is very important. I do a dye extrusion. I force the grease out into a little flow channel, and I measure how much force it takes to make it move. That's the consistency. Has that changed? Does it take more force than the new grease? Does it run out too readily, like it's going to leak out of the machine? I can measure that property. I can look at the color. Part of the reason the manufacturers put the dye in there is so we can keep track of what we have, because you can't be mixing these things. And when you're pumping in the blue grease and the purple grease comes out, some red grease was in there at some time, okay? So colorimetry is actually a very powerful tool, and we can test that for the new grease and compare it to our used greases, see where that is. This was the manager that said, I get about a year out of my belts before I change them. You can't expect much more than that. It's just about having low expectations. Here's one that was a 2-belt drive in a research area at the NIH, and it required a shutdown every 2 weeks for belt replacement. Why, though? Why did he get stuck doing that? It was a poorly made base. It was these thin, bent pieces of metal expected to hold incredible forces in a jacking bolt arrangement to get the proper tension out of those belts. And it was never going to be able to achieve that. We designed a new base plate with gussets and jacking bolts, made it easier to align it properly, held that tension, and kept it where it needed to be. Ended up extending the life to 5 years from 2 weeks. 5 years from 2 weeks. So what are our best practices? Inspect belt drives utilizing periodic condition monitoring. A strobe light is a fantastic tool. You can slow the motion of each of the shifts. It's sometimes hard to get the belt to stop moving, but you can see some features on the belt. You can at least get it kind of flashing at you. If you blink real fast, you can figure things out. But the strobe light's very helpful. We can look for damage. We can look for shaft speed determination, vibration analysis using the measured and calculated frequencies of the motor shaft, the driven shaft. If it's a variable frequency drive, you got to see where your VFD is, right, and kind of line that up. Look for belt bearing fault frequencies and the belt number of belt rotations. Use infrared thermography. You saw that picture at the beginning. That launched 30,000 LinkedIn likes, right? That was the infrared image, and that's really helpful. You can see belt slippage. And then grease analysis to look for these things to optimize and so forth. Use proactive maintenance to address the design deficiencies. If you don't have a good base, you'll never get to long belt life. You've got to go back and fix it. You have to identify the design deficiency and fix it. Look for mismatched belts and shivs. If they are not the same design, you're going to get slippage, you're going to get wear out, you're going to get a lot of heat too. Maybe you can enhance the belt style or design to better align to the application. Do condition-based grease lubrication frequencies and quantity. Remember I said optimize your greasing. Improve your base design with jacking bolts. Make it easier to get precise alignment and tensioning. Okay? And doing these things, improving alignment and tensioning, utilizing precision maintenance tools, got the NIH the Uptime Magazine Award for PDM Program of the Year back in 2006 from this conference. So it's proven, it's been peer reviewed, and it can work.